In this video, I'll talk about the homolytic and heterolytic bond breaking, or also called homolysis and heterolysis bond cleavage. Regardless whether it's in a homolytic or heterolytic bond breaking, any bond breaking is going to be an endothermic process where it actually requires energy. So I can say that would be an endothermic, that where the delta H for that particular process where you're breaking the bond is going to be in a positive value. Now, what's really the difference between the homolytic and heterolytic? Some of the key differences that in heterolytic bond breaking, when you do so, you actually make a cation and an anion. So another way of saying you're making the ions there, but in case of a homolytic, you actually make radicals. And then the heterolytic bond cleavage actually works on the difference of electronegativity, where two atoms will have a significant difference in the electronegativity, and that's really the foundation for breaking the bond homolytically. But on the other hand, the homolytic bond breaking will typically takes place when they have almost similar or the same electronegativity values. And this is where there's really not any polarity going on in the bond, and it would be hard to break it heterolytically. So then let me kind of give you an example in terms of drawing the arrows as well. So suppose if I have a bond that's between an A and B, and if B is more electronegative, let's say if B is more electronegative than A, then I can go ahead and break this bond heterolytically, where when this bond gets broken up, it goes the B takes the lone pair with it, and then A makes the positive charge, and then B eventually ends up getting in a lone pair, and which possibly would have a negative charge, because you also got to make sure you're conserving the charges. So this is in a case where B is more electronegative than A. But then I can have in a scenario where it's literally the opposite. What if A is more electronegative than B? So then if A is more electronegative than B, when the bond breaks, it's going to go with the A. So whoever is more electronegative, or another way of saying whoever is kind of greedier, takes that bond with it. So in that scenario, you actually get a negative charge along with the lone pair on that A, and B would get a positive charge. So this would be the case if A is more electronegative than B. But now let's suppose you run into a scenario where both A and B, or the atoms that are making the bond, they having a similar electronegativity values, or even like the same electronegativity values. Then in that case it becomes hard to break that bond heterolytically, but rather that bond would be now broken up homolytically. So in a homolytic bond breaking, you kind of break the bond where one electron goes on to one of the atoms. So when you show the electron movement, and if it's only one electron, you show within half an arrow. So if you focus on the previous cases where we were breaking the bonds heterolytically, and if both of the electrons moving to one atom after the breaking, you show in a full-headed arrow there. But in homolytically, if that's what's happening, you want to show a half-headed arrow, and then the other one would be going on to A, basically. So something like that. So what I get at the end of the day, I get A with an extra electron, and I get a B with an extra electron. So anytime you get those extra electron that is technically unpaired, those are called radicals. So you are making radicals whenever you're doing an homolytic bond cleavage. But in case of heterolytic bond cleavage, you will be doing making it in anions and cations. So where do you really see some of these examples? Like I can talk about somewhere, maybe I have two chlorines right there. I'm trying to break the bond between the chlorine, and when I'm breaking the bond between the chlorine, and I know there's already three lone pairs on each of those chlorines. Now, both of those chlorines has obviously the same electronegativity value, so I would not be able to break it heterolytically, but rather I will be breaking this bond homolytically. So when I break this homolytically, one electron goes on to one of the chlorines, and the other electron goes on to the other chlorine. So what I really get at the end of the day is two chlorine radicals. So I can go ahead and show those three paired electrons like we had earlier, but now I'm going to have one electron that's going to be unpaired, and that electron that's going to be unpaired, that's what really makes this a radical. That's one way of expressing it. You may also see chlorine radical being written as 2 chlorine, and then they will just draw one electron. That's assuming that you already have three other non-bonding electron pairs on the chlorine, so you don't necessarily have to draw those all the time. So that's an example of an homolytic bond breaking. But now, if you want to do an heterolytic, I can talk about something like, suppose I got then a carbon and a chlorine bond here. So now I know the chlorine is more electronegative, so I'll have a partial negative charge here, and carbon is less electronegative, so we'll have a partial positive charge here. So I do see an electronegativity difference here, and because of that, I can break this bond heterolytically. So when I'm breaking this bond, the the bond electron always goes to the atom that is going to be more electronegative. In this case, it's going to be the chlorine. So now I already have three electron pairs on the chlorine, but now you get another extra pair of electrons after the bond was broken. So now you have four, and you get a -1 charge on this chlorine, which makes it a chloride. Now, what's left behind, I got this carbon who all of a sudden becomes electron deficient because that bond that was with the chlorine is not there anymore. So now this carbon already only has three bonds left. Remember, there's one hydrogen that you don't have to draw. So before it has four bonds, but now this carbon would have only three bonds. So I want to go ahead and put a positive charge there. So that is how you make an really an anion and the cation in this case. And when you have a carbon with a positive charge, you call it carbocation. And if you have a carbon with a negative charge, you will call it carboanion. And what you want to notice here that the net charge on this reactant was zero, and the net charge on the product is still zero, even though you have chloride with a -1 charge and carbon with a positive charge. But at the end of the day, when you put it all together, the net charge on the product side is still zero. I can also talk about, let's say, an example where maybe I have a carbon and lithium connected. So in this particular case, even though it's like an ionic bond, but if I look at electronegativities here, carbon is going to be more electronegative, which because it's in a non-metal, and lithium is actually in a metal, so it's going to be less electronegative. So when I go ahead and break this bond, I would have this bond kind of goes onto the chlorine in this case. So what I get at the end of the day, I get an extra pair of electron on that carbon, which gives it a -1 charge, and then I get lithium within a plus charge. So that's how you make this carboanion in this case. So it really depends on how you're going to be breaking the bond, and at the end of the day, what is really the driving factor is what really their electronegativities are. And regardless whether you're doing heterolytic or homolytic, you still need energy. And a lot of times for the homolytic, you and wherever you have the radicals being created, you would see those reactions are either being done under UV light or just the heat, or maybe you need a stimulator that already has a radical in there. But even to create the radical in the beginning as like a stimulator, you still need ultraviolet light.